A very good evening to one and all, and welcome to the special public lecture today, where we have with us Professor Sir Colin Humphreys from Queen Mary University, London. And he's talking to us the topic Graphene and Gallium Nitride from basic science to manufacturing devices. And this special public lecture is jointly organized by the National Academy of Sciences, India, Delhi chapter, and the Upadhyaya College, University of Delhi under the aegis of the DBT Star College program. At the outset, I would like to thank the National Academy of Sciences, India, which is the oldest science academy of India, and Professor Anurag Sharma, who's the chairperson of the NASI Delhi chapter, and the president of NASI, Professor Joy Cutter. So before inviting Professor Colin to deliver his talk, let me briefly introduce him to all the attendees. So he's a material scientist who has carried out valuable work on the electron microscopy of semiconducting materials. His world-leading research on gallium nitride has resulted in a substantially improved understanding of this important material with a wide range of technological applications. In addition to its potential use within transistors as a next-generation alternative to silicon, gallium nitride emits a brilliant light that makes it an ideal candidate for use in energy-saving LEDs. He has pioneered the development of low-cost, high-efficiency gallium nitride on silicon LEDs, which are now being manufactured based on his patented research. In parallel with his scientific career, he has devoted considerable time and effort to communicating material science to lay audiences. This work led to his being awarded a Commander of the Order of the British Empire in January 2003 for services to science as a researcher and communicator, followed by knighthood in the year 2010. Since 1996, he has been also the Fellow of the Royal Academy of Engineering. With these words, I now invite Sir Humphrey to kindly deliver his talk. Please go ahead, sir.
Fine. Thank you very much, Manoj. It's a great pleasure to be here and a great honor to be giving this talk. And let me explain my three university appointments, as it were, on the first page here. So I'm a professor at Queen Mary University of London, and I also set up a company called Paragraph, and I'm the chief scientific officer at Paragraph. And I was at the University of Cambridge, and I'm an emeritus professor at Cambridge. And it's really a very great pleasure to be here. Thank you. Please. Next slide, please. So this, as it turns out, this talk is very relevant and very topical because, as you will know, recently, just in December, the Indian government had a very big program that they announced for the development of semiconductors and display manufacturing in India. And it's got a very big budget for this. So in Indian rupees, it's 760 billion, and that's greater than 10 billion US dollars. So this huge program on semiconductors. And then just a few days ago, in January 2022, India's first Graphene Innovation Center at the University of Kerala was announced. And it was actually said in the press release I saw that graphene will replace indium and bring down the cost of OLEDs in devices. And at the end of this talk, I say that we've recently been working on this and demonstrated that this can be done. So it's a very good time for me speaking to you because it really coincides with these major initiatives of the Indian government, which you'll already know about. Next slide, please. So I'd like to thank you to a number of people, to Manoj, who's the program coordinator, and it's been very helpful. It's been a pleasure to interact with Manoj, and it's a wonderful program that you have here of talks. And I'd like to thank, as he has done, the National Academy of Sciences, Indian Delhi chapter, the IAEE Electron Device Society Delhi chapter, and then the University of Delhi, the Deen, Dayal, Upadhyaya College. Also like to thank my funding sources. So Engineering and Physical Sciences Research Council in England, they funded my gallium nitride research and initial graphene funding, and then also Innovate UK, who funded some more of the graphene research I've been doing. And again, it's a great pleasure to be here. So what are the most important materials innovations? Well, one way of answering this question is, what materials have won Nobel Prizes most recently? And in 2010, two Russian scientists working at the University of Manchester, Gaiman and Novoselov, they won the Nobel Prize for groundbreaking experiments regarding the two-dimensional material graphene. And then in 2014, three Japanese scientists won a Nobel Prize for the invention of efficient blue LEDs, which are based on gallium nitride. And the citation said it has enabled bright and energy-saving white light sources. It is unusual for materials to win a Nobel Prize, yet here we have gallium nitride and graphene winning materials. So these are two of the most important recent materials developments that have happened in the last 20 or 30 years. Next slide, please. So I've been very fortunate to be involved in both of these. I'm going to tell you something about my research on these in this talk. So in this talk, I'm going to go from basic science to exploitation, which I like to do in my research. This is the wonder of working on materials research, that you can really go from basic science right through to exploitation, which I've been doing. And these two materials have been and will be of huge benefits to this society. So we'll see some of this in this talk. They'll save lots of energy, they'll save carbon emissions, create jobs, save lives and improve our health. So these two materials have remarkable applications. This is the content of my talk. I'll start to talk about gallium nitride on silicon LEDs and also MicroLEDs and electronic devices. And after talking on gallium nitride, I'll move on to graphene, talk about the high expectations everyone had of graphene to start with, then the problems with applying graphene to electronic devices, the new solution we have, we've got a new growth method for graphene, growing using MOCVD, the first in the world, I think, to do this. And then our first product, which is a graphene magnetic hall sensor, which we're manufacturing, and then graphene OLEDs, which we've just made. So that this is really very up to date. My collaborators in Cambridge on gallium nitride were Rachel Oliver, Menno Kappers, Dan Zhu, Clifford McAleese, and many more people. And then I moved from Cambridge to Queen Mary in 2018. So if we go back to 2002, gallium nitride LEDs were really expensive. They're £50 each. So we think of American dollars, they're about $50 each. And I know Prince Philip in Buckingham Palace, he could afford them. And he was one of the first people to put gallium nitride LEDs in Buckingham Palace. And that was in 2002, but very expensive. But most houses, of course, couldn't afford that. And then I had the idea of trying to reduce the costs, and to do that, to grow on 6-inch silicon wafers, because silicon's much cheaper than the substrates which were used for gallium nitride LEDs. So the substrates for gallium nitride was sapphire or silicon carbide, very expensive, grow on silicon much cheaper. And also if you have large area wafers, 6-inch diameter, that's then much more, it reduces the cost compared with 2-inch wafers, because it's more or less as cheap to process a 6-inch wafer as a 2-inch wafer. You get many more devices on a 6-inch wafer. So in 2002, I took on a new research student called Matt Charles. His PhD project was MOCVD, growth and characterization of 3 nitrides on silicon. MOCVD is an acronym, or the first letters of metal organic chemical vapor deposition. And I put it in bold in this slide because it's the experience we had with gallium nitride using MOCVD, which enabled us to think of using MOCVD for growth of graphene instead. And so we'll come on to that in the second part of the talk. And so in 2002, I had a 3-month project from the UK EPSRC. And this project was called Exploratory Proposal to Grow and Characterize Gallium Nitride on Silicon. And it was £50,000 or $50,000. And we had this exploratory grant to see if it looked feasible. And it looked feasible. And then I got a bigger grant to actually grow properly as much as we could on 2-inch and 6-inch silicon wafers. And Matt Charles achieved this in his PhD, but the efficiency was not very high. I think the efficiency was about, internal quantum efficiency was about 15%. And we really needed it to be higher than that to have something which could be exploited and to compete with the tungsten light bulbs in people's homes. Next slide, please. So these were the challenges of growing gallium nitride on silicon. Because as I said, the standard gallium nitride LEDs you could buy then, which were very expensive, were grown on sapphire or silicon carbide. The first challenge is this very high lattice mismatch of 17%. And this gives you a very high dislocation density. When you grow on sapphire or silicon carbide, the lattice mismatch is much less, and the dislocation density is much less. And that lower dislocation density doesn't quench the light emission, but this high dislocation density does reduce the light emission. So that's a problem. The second problem is this extremely large thermal expansion mismatch between gallium nitride and silicon. The thermal expansion mismatch is 54%, which is huge. And you grow these devices at about 1,000 degrees centigrade. So when you cool down from this temperature, then the gallium nitride is in tension and it cracks. When you have gallium nitride on sapphire, you grow at a similar high temperature and you cool down, but the gallium nitride on sapphire is in compression. It has a positive thermal expansion mismatch, not this negative one. And so it doesn't crack. And so this is a major problem you have to overcome when you grow on silicon. And then the third problem when you grow gallium nitride on the silicon is that you get a gallium silicon eutectic formed called melt-back etching. You can't then grow devices on this. Whereas when you grow gallium nitride on sapphire, you don't get this melt-back etching. So these are three problems you have to solve if you're going to grow gallium nitride on silicon devices, and you need really basic science to solve these three problems. Next slide, please. So what you have to do is to grow a buffer layer to stop the gallium nitride. So you don't grow directly gallium nitride on silicon because you get this melt-back etching. You have to have a buffer layer in between the gallium nitride and the silicon. And the buffer layer that's used is aluminium nitride, and that doesn't react with the silicon. So you then grow the aluminium nitride on silicon. And what's then important is to optimize the quality of the aluminium nitride on silicon interface, because that then determines the quality of the nucleation layer of aluminium nitride you have. So we studied this. Next slide, please. And we studied this and we optimized the quality of that interface. I should just say before this talk started, my talk was huge with all the images I had, and I had to withdraw some of them, and so I had an image of the interface just to show you could really optimize it. So this is a second problem now. This is a difference in thermal expansion coefficient between gallium nitride and silicon, and this is due to cooling down from the melt, and you get cracks. And what a number of people were doing, other people in the world were trying to do this at the same time. And they were patterning the silicon substrate to guide the cracks. And we decided not to do that, because if you're thinking of manufacture, patterning the silicon substrate is an additional manufacturing step. It's good to avoid if you can. So we grow on unpatterned silicon substrates, and then we deliberately introduced compressive strain layers. Compressive stress layers. So we did use aluminium gallium nitride to compensate the tensile stress you get on cooling. So aluminium gallium nitride has a bigger lattice parameter than aluminium nitride. So when you grow aluminium gallium nitride on, aluminium gallium nitride on silicon, and then you grow aluminium nitride and gallium nitride, you're introducing compressive stress to compensate this tensile stress. And what we found was, this is stress management, and what we found was we introduced 4 graded layers of aluminium gallium nitride. So there's a lot of trial and error here to see what worked. But this huge compressive stress that you were introducing this way, you can exactly compensate the tensile stress. So say it the other way. You introduce compressive stress to exactly compensate this tensile stress, so the wafer doesn't crack and it remains flat. And then this is the next problem. You had the third problem, which we had to solve, was this large lattice mismatch, which gives rise to a high dislocation density. And so what we did here was to introduce a silicon nitride mask, which was grown in situ in the reactor. And this was less than 1 monolayer thick. So what do I mean by less than 1 monolayer thick? I mean, it's a monolayer thick, but it has holes in it. And these holes are formed naturally. So if you stop the growth before you have a complete layer of silicon nitride, then you have an incomplete layer which holes in. And this silicon nitride mask, you put on top of the gallium nitride, and then you grow some more gallium nitride. And the gallium nitride grows through the holes in this mask. But can we have the next slide, please, which probably just shows this. Yeah, so this shows what you're doing. So this red color here is the mask. It's a silicon nitride mask. Underneath that, we have gallium nitride with all these threading dislocations propagating upwards. And well, thank you very much for the points. That's excellent. And when the dislocations hit the mask, then they stop. They won't propagate through. But when they hit the holes in the mask, they propagate through. So you've immediately got quite a big reduction in dislocation density just by having the masks. But we can reduce it still further because when we start to grow on top of the masks, we alter the growth procedure, so we alter the growth mechanism. So underneath this silicon nitride layer is layer by layer growth of gallium nitride. Above the layer, we have island growth, so we can change the growth and you have island growth, and you have these faceted islands. And when the dislocations which come up through the hole, when they hit the side face of the facets, they bend sideways. And if you're lucky, then a dislocation which comes up and bends sideways interacts with a dislocation which comes up from a neighboring hole and bends sideways in the opposite direction. And these two dislocations come together and they either annihilate or they form one dislocation. And this is another dislocation reduction mechanism. And you may think that's an extremely unlikely process, but actually it's not that unlikely. And it really gives you a significant reduction in dislocation density. So the next slide, please. So I'm sorry, this is one of the slides I had to reduce. I'll just tell you the results. So we can reduce the dislocation density by 2 orders of magnitude using this method. And so we got down from something like 10 to the 10 dislocation density to 10 to the 8. And at 10 to the 8 density, we have brilliant light emission. And what this slide shows you is a 6-inch wafer of gallium nitride on silicon and the LEDs on the top. And these different structures on the LEDs are different test structures of the LEDs of different size. And this is the first 6-inch fully processed wafer on a 6-inch processing line of gallium nitride LEDs in the world. And this was done in 2009. And if you look at the picture on the top right, that's a magnified image, a part of this 6-inch wafer. And then the bottom right picture shows 2 electrodes are being applied to an LED structure, and you can see bright light being emitted. It's actually blue light that's being emitted, but it's so bright it's saturated the detector, so it looks like white light. And these are indium gallium nitride LEDs, and they all worked on this device. So we're very, very pleased. And we didn't have a 6-inch processing line in Cambridge, but this was done at a company called RFMD. So, and this was the first demonstration of 6-inch gallium nitride LEDs on a 6-inch wafer. Next slide, please. So what we did, we tried to exploit this, and we set up a couple of companies. And I set this up with a postdoc and a research student, these 2 companies. And then a British company called Plessy acquired these companies in 2012. And people said to me, it's going to take 2 years to transfer the technology from your laboratory into industry. And Plessy, very sensibly, they hired 3 of my postdocs, and they transferred the technology not in 2 years, but in 6 weeks. So this can be done. And so we did it very quickly. And then Plessy manufactured low-cost gallium nitride on 6-inch silicon wafers at their factory in Plymouth. They reckoned that the cost reduction was a factor of 5 times cost reduction compared with growing on sapphire or silicon carbide. And this was the first manufacturer of gallium nitride LEDs in the UK. And they sold 2 million LEDs in 2014. And they sold them to other companies. They sold them to companies like GE to put in their light bulbs, and then companies around the world put in their light bulbs. And it was also the first commercially available GaN LEDs on silicon, on 6-inch silicon, anywhere in the world. So this was a really quite quick exploitation route. Next slide, please. And now, if we come right up to date, Plessey are now making GaN-on-silicon micro-LEDs. And this is based on our patented technology, because we took out a patent and then Plessey acquired our patent. And in 2020, Facebook decided that they were very interested in micro-LEDs for displays. And these were displays for their augmented reality headsets. And Facebook looked around the world for the best company to collaborate with on micro-LEDs, because at the moment there's maybe 10 companies trying to make micro-LEDs in the world, gallium nitride micro-LEDs in the world, and they chose Plessey as the best. And Plessey are using our gallium nitride on silicon technology for this. And then if we look a bit to the future, the next generation displays for televisions, etc., they may well be gallium nitride micro-LEDs, because we know we've got small displays you can make at the moment, and big displays, of course, you need for television. So this needs scaling up further. But we know that the picture will be better and the energy consumption is reduced significantly. So, you know, OLED screens are the latest screens, and they're lower energy than liquid crystal display screens, but the micro LEDs will be lower energy consumption than the OLED screens. And you're just using each micro LED as a sort of pixel. So very, very small pixels for the TV screen. So you don't see the individual LEDs, that's why they're micro LEDs. And we think by micro LEDs, something like a micron across. Those are really very small. But in the future, look into the future, you could have a much better picture, a much lower energy consumption, maybe 10 times lower energy consumption. So you know, this is all very good news for saving carbon emissions and saving energy. Next slide, please. So let's look at the energy savings from gallium nitride. For low-cost LED lighting, the savings of electricity are 15%. So this means if India, all of India goes to gallium nitride lighting, I know there's a lot of gallium nitride in India, you're saving 15% of your total electricity consumption by doing this. And this 15% figure comes from the US Department of Energy, who've worked it out very carefully. So it's a huge saving. Now, I haven't got time to talk about silicon-based power electronics. The LEDs, and these are being produced and sold now. But there's a further 10% saving on if you replace silicon power electronics by gallium nitride power electronics. And so, for example, gallium nitride transistors, they give you that a gallium nitride transistor saves 40% of the energy compared with a silicon transistor. And you save that energy, and also you save on size and weight. So let me just digress. When you go to a shop and you buy a computer, a PC, a laptop, you may want it to be very light so it's portable. And so you buy this very light laptop, and then you get the package from your shop and you carry it away, and it's rather heavy. And it's heavy because, well, it used to be heavy because of the power supply. So the power supply used to be like the size of a brick. And then, the silicon power supply, the transformers in the power supply were shrunk. But the now modern ones, they're shrunk still further because of gallium nitride. There's huge weight saving now on the power supply, on the transformer from the mains to your computer. And the total electricity saving is 10%. Now, what's remarkable is that the total electricity saving you use from this one material, gallium nitride, is 25% of total electricity use. It's quite a remarkable figure. So it means if the whole world went to gallium nitride LEDs and gallium nitride electronics, you could save 25% of global electricity. It's almost unbelievable, but it's actually demonstrated. It's demonstrated to be 15% for lighting, and for the electronic devices like transistors, is a total overall saving of 10% electricity. So huge efficiency gains. And if the electricity you're using comes from fossil fuel power stations, and most of the electricity in the world still comes from fossil fuel power stations, then you get 25% carbon dioxide savings as well. So there was a review done by Goldman Sachs of green energies, and Goldman Sachs says gallium nitride has done more to save energy than anything else in the world, right? It's done more actually than solar power or wind power. So, it's a remarkable material to be working on. Next slide, please. Right, so we're now changing subject and we're going to graphene. And as I said, Gein and Vossilov got the Nobel Prize for graphene regarding the two-dimensional material graphene. And it's a two-dimensional material because it's a two-dimensional network of carbon atoms. But I'll just say in passing, it is, I believe, a mistake to think of graphene as a two-dimensional material. And I say that because you've got pi electrons above and below this two-dimensional plane. So it's actually, when you're thinking of using graphene, it's rather important to remember you've got these pi electrons there, and it's actually a three-dimensional material. And you can define elastic tensors, 3D tensors, for example, for stresses and strains in monolayer graphene. So just think of monolayer graphene as a 3D material, although it's called a 2D material. So the plane of atoms is just a 2D material. Pi electrons above and below give it some thickness. And the thickness of a single monolayer graphene is about 3.4 angstroms, if I remember correctly, something like that. And you can define the thickness. I shall just say this: if you have a graphite and you measure the thickness of a block of graphite, and then you count the layers, the graphene layers in a block of graphite using electron microscopy, say, and let's say you've got 100 layers in the block of graphite, and the block of graphite is 34 angstroms thick, got 100 layers, and each layer is 3.4 angstroms thick. So that's one way of measuring the thickness of graphene. It's sometimes in England called carbon chicken wire, because when people have chickens in England, they surround the pen with chicken wire, and the chicken wire has a hexagonal network, and it looks a bit like the drawing of the single layer of graphene. And graphene is the first material in the world in which all the atoms are in a single plane. Next slide, please. So these are my collaborators on graphene. I'll just explain what this means. So when I was at Cambridge, I had Simon Thomas and Ivor Guiney as two postdocs, and they, as I'll tell you in a moment, they developed the technique of growing MOCVD graphene, and then they've both moved to graphene. And Simon Thomas is the CEO, Chief Executive Officer of Paragraph. And I should say, this is an important message. When we set up Paragraph, I was the chairman of Paragraph, and that worked for the first 18 months or 2 years. And then someone said to me, Colin, you're not really a company chairman, you're really an academic. And now you've had wonderful progress for the first 2 years, but now you need a company chairman who's got experience of companies. And I could see the wisdom of that. So, some academics who set up companies, some are great actually for actually running it for years and years, but many academics are not good for running companies. So you need to, if you set up a company at a certain stage, you need to think, am I the best person to chair this company and run this company? So I'm now the chief scientific officer there. And then recruited a number of other people, many other people actually, and I'll talk about that in a moment. But Hugh Glass contributed particularly to what I'm going to talk about today. And then at Queen Mary, two postdocs, Yue Sun and Zichao Wang, contributed to this work, and then two other professors at Queen Mary, David Dunstan and Bill Gillian. So they've all contributed to what I'm now going to talk about, our work on graphene. So graphene was isolated in 2004. People got the Nobel Prizes, Gaiman and Vossilov. And what they did, and you'll know this, I think, they put sticky tape on graphite, a block of graphite, some sticky tape on both sides. It's sometimes called sellotape or scotch tape. And they pulled it apart. And so they split the graphite into two. And then they put another piece of sellotape on and pulled it apart again. And they kept on doing this until they got down to a single monolayer of graphene. And so it's a really nice concept and a nice experiment to do. And then they performed experiments on this. And these experiments are really difficult because a monolayer graphene is transparent. So just think you've got this monolayer graphene on a piece of sticky tape and you can't see it. But they did experiments. They measured the mobility of the carriers in graphene, and they measured the electrical conductivity. And it's brilliant experiments to actually put electrodes onto something you couldn't see. So some people say they got the Nobel Prize for using sticky tape. Well, no, they didn't. They got the Nobel Prize for using sticky tape and then doing these experiments. And then this monolayer of graphene had the most remarkable properties. Otherwise, they wouldn't have got a Nobel Prize. So that's why they got the Nobel Prize. And when you peel off, it's called exfoliation, when you have the sticky tape and peel off layer after layer, you get quite small graphene flakes because you may have grain boundaries in the graphene and they may break at those positions. And graphene flakes and powders are now being used to add to car tires, where they're said to extend their life, and add to paint, and add to concrete. They said it makes it more resilient, and even added to tennis rackets and running shoes. And I think, to be honest, some of these applications may be true applications. So for car tires, graphene is a very good conductor of heat and electricity, and so it may well keep the car tires cooler and so extends their lifetime. So I think that's probably a real application. I am not sure about tennis rackets. They're just added to the sort of piece of wood that divides, a sort of Y-shaped piece of wood on a tennis racket. Can't do a Y-shape, but anyway, that's where they're added. And it's hard for me to think they have much difference, but I think they give the player a psychological benefit. So let's say you're playing a tennis game with somebody and he says, I've got a graphene tennis racket. Then you immediately think, gosh, can I beat some of the graphene tennis racket? And then if he wins, you go out and buy yourself a graphene tennis racket. So people can charge higher prices for these things, but they're not necessarily better. But if we're going to make electronic devices, you can't make them with these small graphene flakes. And actually, this peeling process is quite laborious, and it takes about 45 minutes to get down to a single layer of graphene. So you need large area graphene if you're going to try and make electronic and optical devices like sensors and transistors. Next slide, please. So these are the properties of the exfoliated graphene flakes that Gaiman and Novosela found. Very high electrical conductivity, said to be 1,000 times better than copper. Because of that, very low resistivity, so that promises very low power consumption, because very low resistance devices. Very flexible, so you can have flexible electronics. High thermal conductivity, promises increased device performance. And as an aside, the gallium nitride electronic devices, which are being used at the moment, you can only use them at about 1/3 of their theoretical limit, because otherwise they get too hot and you can't dissipate the power. So power dissipation, you can't dissipate the heat. Heat dissipation is really critical. And with gallium nitride devices, you promised increased device performance because of this high thermal conductivity. And they're highly transparent, 97% transparent to visible light, a single layer of graphene. And what's remarkable about graphene is it just doesn't have one of these world-beating properties. It has the whole set of them in a single material. And so it's a unique material to have so many special properties in a single material. And it's therefore has been called the wonder material. Next slide, please. And so here's graphene, the wonder material. And so lots of industries quite reasonably thought that this could be transformational for their industry. And so Intel have invested $750 US in graphene research, IBM $3 billion US, Samsung $2.2 billion. And I'm told they've largely stopped doing this because they haven't been able to scale up. So this has been the problem. You have these tiny flakes of graphene, remarkable properties. To make transistors, you have to be able to scale up, and they have not been able to scale up. Next slide, please. So yes, where are all the products? And this shows you some of the newspaper headlines. So on the left, this is from the newspaper of the World Economic Forum. And there's this heading, graphene can soon make your computer 1,000 times faster. I think this headline goes back to something like 2012. And of course, 10 years later, we do not have graphene computers 1,000 times faster. So there's this huge hype, which hasn't happened. In the middle, Bosch finds graphene magnetic sensor 100 times more sensitive than silicon. On the right, graphene filters change the economics of clean water. And again, as far as I'm aware, that hasn't happened. They haven't changed the economics of clean water. So you can show these remarkable results at the laboratory level with tiny flakes of graphene. The challenge is to scale up. Next slide, please. And Bosch did create a graphene Hall sensor, magnetic sensor, in 2015 from flakes of graphene, and they assembled it by hand and they found it had, they said, 100 times the sensitivity of a silicon Hall sensor. But this is what they said in their press release. They added, it's unlikely to compete for 5 to 10 years due to the current lack of large-scale, wafer-based and transfer-free synthesis techniques. So basically, they said it's got remarkable properties. We cannot manufacture like this until we get these large-scale techniques. And so what happened was, at that time, I had these 2 senior postdocs in Cambridge, Simon Thomas and Ivor Guinea, and I set this to them. I said, look, we need some way of making a large area graphene. And because in Cambridge, we had MOCVD equipment for which we're using for graphene work, then we thought, yes, so we're using gallium nitride work. So that's going to go. We were using Cambridge three MOCVD kits for gallium nitride research. Can we use MOCVD for graphene research? And we thought at the time we were first people to think about this. But in fact, we've subsequently learned that's at least one other group have thought about this, but they couldn't make MOCVD work, so they never published anything. We got it to work. So I said, when I say we got it to work, it's us, my 2 postdocs got it to work. And this was in 2015, and it was patented. And we grew the graphene directly onto a sapphire substrate. And so when you have CVD growth, chemical vapor addition growth, which was the other way of making large area graphene. So that was the way people were trying to make large area graphene by chemical vapor deposition, CVD. They had to use a metal catalyst to decompose the growth gases like a CH4, and copper is typically used. And then that copper contaminates the graphene that you grow. And then you grow by CVD, you grow the graphene onto copper. And then to use it, you have to transfer it onto a more useful substrate because it's quite hard to make graphene on copper devices. And so what we do with MOCVD was to grow directly onto sapphire and other substrates. And we don't have we don't need a metallic catalyst to decompose the growth gases. So we have what seems to be a very promising new technique for growing graphene, which may be able to grow next generation devices. So we set up a company called Graphene to exploit this research. Next slide, please. And we raised funding in October 2017. It took time because no one believed us, right? So people had invested a lot in scaling up graphene, investors had, and they'd lost a lot of money because it hadn't happened. And so when we went to them saying, we've got a new idea to grow large area graphene, they sort of laughed at them and said, no, we're not going to waste more of our money investing on you. So anyway, we've persuaded companies to invest, or investors to invest. And we got seed funding in October 2017. And we moved into premises in 2018 with 2 employees, and we now have 75 employees. So this has been tremendous growth for us, and we've been very fortunate to do this. Next slide, please. And this is a tip for any of you wanting to set up companies. So we spun out from the University of Cambridge, and the first place we looked for premises was the Cambridge Science Park, which is the most successful science park in Europe. The problem there is that it's not one science park. There's a number of science parks in Cambridge, and could we possibly go back? I'm sorry, that's on the slide. Thank you very much. And the premises, the science parks are almost full, and they're very expensive. So the size we wanted initially, our rent that would be charged was £100,000 a year, or think of that as $100,000 a year. And so we toured around the country, and then we found in a village north of Cambridge called Somersham, a farmer had put large sheds up on his land, and he called it an industrial park. And he said, come and use my industrial park. And the rent of these sheds was 1/10 of the rent in the Cambridge Science Park. So if any of you are thinking of being entrepreneurs and setting up a company, you don't need a big, expensive building. You can have a shed. And this shed was an empty shed, and it had no electricity and no water. And we got the electricity brought in from a power station, nearby, and we got water brought in. And then we built nice buildings inside this shed. So we got carpeted offices, we got clean rooms inside. We just put them inside the shed, and so it works very, very well. And we've got low cost accommodation. And our goal is to deliver scaled up graphene. Next slide, please. So just to say again, no metallic contamination, no transfer problems. With any luck, something else should come up. Right, excellent. Uniform large area layers, 100% substrate coverage, functionalized. So whenever CBD grows, you can dope while you're growing. You just have another precursor source. Say if you want to grow with nitrogen, say you have nitrogen precursor source. If you want to grow with boron, you have boron. So we can dope while we're growing, and it's suitable high volume device production, and it's suitable, we believe, for these devices and sensors. And our first product is this graphene Hall effect sensor. Why did we choose that? Because our investors, we told them the Bosch story, that they said you couldn't make this unless you scaled up. And our investor said, okay, you go and make a graphene Hall effect sensor. And so we did our first product, and it's made on sapphire. And we had no idea what the properties will be like. So I'll now tell you the properties of our graphene Hall effect sensor. Next slide, please. So, okay, what is a Hall effect sensor? I think many of you will know this, so let me just go through this very quickly. On the slide, you can make Hall sensors from many different materials, from semiconductors or metals or anything. The Hall effect works, but they're mainly silicon Hall effect sensors. And this slide shows a Hall effect. So you have a slab of material, and a magnetic field is coming up through that slab at right angles. This is like this magnetic field B. And then you apply a voltage, which is called voltage in, and an electric current then flows in a perpendicular direction to the magnetic field. And a Lorentz force acts on the electrons, and it moves them to one side. And that creates a Hall voltage in the third perpendicular direction, and you can measure the Hall voltage. There's a very simple equation which relates the Hall voltage you measure to the magnetic field and the voltage that you applied. And so if you know the Hall voltage because you're measuring it, and you know the voltage you're applying, then you can calculate very easily the magnetic field. So it's a magnetic sensor. On the other hand, if you know the magnetic field, you can calculate the voltage you're applying, or you could calculate the currents passing through. So that's what a Hall sensor is. Next slide, please. And you can, yes, you can measure electric current. So here's a wire flowing. The wire generates a magnetic field, and you can measure that magnetic field with a Hall sensor, and therefore you know what the current in the wire is without contacting that wire. Next slide, please. So Hall sensor sensitivities are measured in units of volts per amp Tesla. A silicon Hall sensor has a sensitivity of 70 volts per amp Tesla. Compound semiconductors like gallium arsenide, you can have quantum well Hall sensors made out of those, and they're the best ones before graphene came along. Their sensitivity is 850, typically 850 volts per amp Tesla. The Bosch graphene flake, if you actually read their paper, was about 1,250 volts per amp Tesla. Our graphene Hall sensor, which is manufacturable, is better than 2,000 volts per amp Tesla. So 30 times better than a silicon Hall sensor. And also it works down to very low temperatures. So it works at less than 100 millikelvins, which is the lowest temperature we've tried. So less than that. And a silicon Hall sensor, the minimum temperature is 230 Kelvin. So that's a huge effect. It means that you can use a Hall sensor for cryo applications. And we're now starting to sell our Hall sensors, and we just sold one or two to IBM, or a few to IBM, and they're using those for their quantum computing, because quantum computing is done at very low temperatures. So they're being used for quantum computing and for other low temperature applications. Maximum temperature at the moment is 400 K, which we believe we can increase. They're highly radiation resistant, so we've had them tested for radiation resistance at National Physical Laboratory. And so this means that they may be good to work in space or in other regions where you've got high radiation. And another property is this huge ability to work in large magnetic fields. So 30 Tesla is the largest we've tried them in so far, so there's no reason it's not more than that. As a semiconductor, Hall sensor is typically 1 Tesla. So that's a huge difference. And again, that opens up new fields that the graphene Hall sensor can be used in, and for example, in fusion reactors. So our Hall sensor now being tested in fusion reactors, which have these very large magnetic fields, like tokamak type reactors. And another remarkable property is very low power consumption. And this is because the resistivity of graphene is so much less than the resistivity of silicon. And our power consumption, in fact, is 1,000 times less than the power consumption of a silicon Hall sensor. So these are really dramatic changes and improvements in the properties of a Hall sensor when it's made from graphene. Next slide, please. And then this is another interesting effect. There's something called the planar Hall effect. And the planar Hall effect, and this was actually, we discovered this when we had some of our devices being tested by CERN. They discovered this. And atom's only 1 atom, graphene's only 1 atom thick. And so the other Hall sensors, even the quantum well Hall sensors, have a finite thickness. And this produces spurious signals from fields which are not orthogonal to the plane of the sensor. And so if you have no planar Hall effect, this improves field mapping accuracy. And this is something which CERN are particularly pleased about. So the tests at CERN, the planar Hall effect is better than 10 to the minus 5 Tesla in a 1 Tesla field. So it's actually negligible, an order of magnitude better than any other Hall sensor. Next slide, please. So this is a summary of the results. So very high sensitivity, greater than 2,000 volts per amp Tesla, very wide operating field range from minus 30 Tesla to plus 30 Tesla. So that means, you know, magnetic field up or down, it doesn't matter. Wide temperature window works from 100 millikelvin up to at least 400 Kelvin. High frequency operation, I hadn't said before, it works up to 100 megahertz. High voltage capability, you can put the mains voltage on, it won't blow it. It blows most other Hall sensors. This, you can put 2,000 volts on and it's capable of withstanding that. Picowatts power consumption, very small power consumption, no planar Hall effects, and parts per billion resolution. And this is a photograph of one of our Hall sensors, an earlier version of our Hall sensors on test. Next slide, please. And this is just an example of a potential use. So CERN are evaluating them for use in the next upgrade, a Large Hadron Collider. So the next upgrade in CERN in Geneva, there's this huge underground ring of magnets. It's 27 kilometers long, going all around, and the next upgrade will have low temperature superconductor magnets operating at liquid helium temperatures, and CERN want to map the magnetic field all around this ring because this is where the particles are accelerated around, and they want 10,000 Hall sensors to map the magnetic field accurately within these magnets all the way around the ring, and they're extremely interested in our Hall sensors for the next generation when they have this upgrade of a Large Hadron Collider. So that's just one example of applications of our Hall sensor. Next slide, please. I'll just tell you, before I move on to OLEDs, I'll tell you a few examples. They're being tested by an aerospace company for aerospace engines, and internal flights. There's a lot of pressure to have all electric engines, again, for saving global warming. And so, well, I say it's a company as Rolls-Royce who make very good aero engines, and they're testing our Hall sensors for use in their aero engines. And you can measure rotor speeds by using these Hall sensors and so on. Another use is in space satellites for detecting when another space satellite comes close that might collide with it, or even we think for mapping the magnetic field from space, because our Hall sensors are very sensitive. So lots of potential applications. Now, let me move on. So this is very recent work. And in fact, the paper was published today. And I'll tell you what it is in the next slide after this one. Let's stick on this slide at the moment. So indium tin oxide is a widely used material in electronics because it's transparent and it's conductive, and that's rare. It's very hard to think of transparent and conductive. Indium tin oxide is, and graphene is as well. That's transparent and conductive. And indium is very scarce. Indium is one of the 9 rarest elements in the Earth's crust. The EU, European Union, has a critical materials list, and indium's on that. Not only is it very scarce, more than 50% of indium comes from one country. So, you know, it's sensitive to political disputes, and you say it says that indium has an irreplaceable role in industry and society. So for sustainability reasons, people want to replace indium. And OLEDs, organic LEDs, usually have indium tin oxide, as a transparent conducting electrode. So people in the past have seen if they can replace graphene with indium, and their results haven't been very good because indium tin oxide is a very good material and it's very hard to replace. Most homes contain indium, so the LED light bulbs you have contain indium because the actual active area, the actual active element is a quantum well of indium gallium nitride. So you have quantum barriers of gallium nitride barriers. The actual emitter is indium gallium nitride, and so all your homes with LEDs in have got indium in. So we really have to conserve indium, and for sustainability reasons. So we've used graphene as the electrode to replace indium tin oxide, and our graphene OLED has an identical performance. We made them under identical conditions. And so that means that in principle, graphene can replace indium can replace ITO in an OLED. And you know, most of the mobile phone screens you have at the moment are OLED screens, and lots of OLED televisions and so on. And so there's a real possibility that we can do this on a large scale. Next slide, please. So this tells you that the paper, it just came out today. And it's published by this. It's joint work between my postdoc Zito Wang, who's at Queen Mary, and then Sebastian Dixon, the next author, and Lockie Yi. They're at Paragraph, and then I'm at both. I've got joint appointment. And then Ivor Guinea and Oliver Fenwick and William Gillen. Ivor's at Paragraph. Oliver and William are at Queen Mary. So it's a real joint publication. And the title is Wafer Scale Graphene Anodes Replace Indium Tin Oxide in Organic Light Emitting Diodes. And this is done at wafer scale. And so again, this is a process which is manufacturable, and it's published in Advanced Optical Materials. So this really does suggest that graphene could replace ITO in many optoelectronic applications. So these are the 2 first things which we're thinking about for graphene replacement: the Hall sensor and replacing indium and indium tin oxide. Next slide, please, which I think is the last slide, conclusions. So gallium nitride on large area silicon wafers are revolutionizing lighting and electronics. I think they have revolutionized lighting. They are revolutionizing electronics. Because of our knowledge of MOCVD, we now are using that to make large area graphene and graphene devices, and we're pioneering this, and we patented this, I say, in 2015. Our graphene Hall sensor is the best performing Hall sensor in the world, and it's manufacturable. And we've replaced ITO with graphene in an OLED, and our MOCVD graphene, it raises expectations that graphene could be used in many other applications like biosensors and like transistors. So these are, it doesn't mean to say it's possible, but it raises our expectations it might be possible. So let me just say it's been such a pleasure to talk with you, and I look forward to trying to answer your questions, if there are any questions.
Thank you very much, Professor Humphrey, for enlightening all of us about, not only about, can I just stop sharing for a while? Yeah. Okay. So thank you very much for enlightening all of us about the various activities which your group significantly have been carrying out over the last 2 decades, I'll say. And you have covered right from gallium nitride, and I rightfully said that in December 2021, India has launched this particular program, And January, they have taken a step forward for the ESDM manufacturing, and definitely they are going to collaborate with lot many companies related to gallium nitride, be it IMEC Belgium or in UK itself. So it is going to open up a big opportunity for the students, researcher, and the faculty members who are working in this particular area.
Yes.
Well, there are few questions. I'll take up those questions which have been shared in the chat section. So the first is do you think that the gallium nitride material anyhow is biocompatible?
The gallium nitride material is biocompatible.
Yeah.
Right. I see no reason why it shouldn't be. Certainly graphene should be biocompatible because graphene is carbon based and our bodies are mainly carbon based. So the graphene could be. The only problem with graphene is if you have isolated flakes of graphene, which are just monolith, they're very thin, and so you have to just worry about very thin materials. Nanomaterials that just maybe have some effect on the body. You have to worry about that. But I think a graphene device, which is encapsulated and so on, will be very, very, very safe, I think, in the body. And I see no reason why gallium nitride shouldn't be. I'm trying to think of a gallium nitride application, but I see no reason why they shouldn't be.
Okay, I'll take up the next one. Apart from MOCVD, is there any other method for graphene synthesis of large surface area?
Right. So the other method which is used is chemical vapor deposition, which is related to MOCVD. So MOCVD is metal organic chemical vapor deposition. The chemical vapor deposition is widely used, but it does have this problem that you need a metal to decompose the gases, which is normally copper, and so the graphene is then contaminated with copper, and you can see the contamination if you do an analysis. And the other problem is you're growing on the copper, so to use the graphene, you have to remove the copper first. The advantage of MOCVD in a sense is, and why we're using it, it is much more. You've got more control than MOCVD. So CVD equipment, the best CVD equipment probably costs you about $200,000. The best MOCVD equipment will cost you $1 million. So it's much more expensive because it has much more control. So you have got more control over the process.
Okay. That's another question by KL Narsimhan. You mentioned that the graphene has high thermal conductivity and good for heat sinking, but graphene needs a supporting substrate, which will limit the thermal conductivity.
Right.
Your comments, please.
Yeah, this is a really good question. So you're quite right. To use graphene, it has to be supported on something. And the wonderful properties of graphene, which have been measured for graphene flakes, do change when we'll support them on a substrate. And so the substrate influences the graphene in various ways. One is it dopes the graphene. So if you like, the Fermi level of a substrate is different from the Fermi level of graphene, and you put them together, you equalize the Fermi level, and charge flows from one to the other. So almost any material which touches graphene will dope it, either positively or negatively, depending on the material. And then the other effect is that phonons in the substrate can influence the conductivity of graphene and the mobility of graphene. So the question is correct. The substrate has a big effect on the graphene.
Okay, I'll take up the second last question, sir. Can't we obtain large area graphene after reduction from graphene oxide? If yes, will it be that much pure so we can go in for industrial applications?
Right. I think people have tried. I mean, people use graphene oxide in applications, and they reduce graphene oxide. It's known as reduced graphene oxide applications, and it has been reduced down to graphene. But I think no one's got good quality large area graphene. So I think that would be still a problem.
Okay. So that's a follow-up question by KL Narasimhan. So for good heat sinking, it is not going to be possible to use unsupported graphene.
Well, no, because the graphene has to be supported on something. But on the other hand, you could think of having a device you want to heat sink and depositing graphene on that. And then that device is supporting the graphene, if you see what I mean. So if you're depositing the graphene on it, so it's worth thinking about that. But you might want to put more than one layer of the graphene on to get larger heat sink.
Okay, so I'll take up the second last question now. At room temperature, graphene has high conductivity. Does it anyhow limit the sensitivity of the Hall magnetic field sensor?
Yes, as we believe that right. So the sapphire. No, sorry. Just so if you look at the equation for the sensitivity of a Hall sensor, it's inversely proportional to the carrier density. So you actually need, for high sensitivity, you need a low carrier density, and so when you go on sapphire, you do get some doping from the sapphire, and it's possible that another substrate would give you an even better Hall sensor. So it's a really good question, because our graphene Hall sensor grown on sapphire is the best Hall sensor in the world, but it's not I think that it can still be optimized further by probably on the sapphire it could be optimized further, but actually choosing a different substrate might make it even better. And that's something that we are sort of looking into, but it's all, at the moment, very good. But yes, the effect of the substrate is really important and critical in the applications.
Okay, I'll take up the last question, sir. In terms of the radiation hardness, which you were talking about, in what way you think that the radiation is going to impact the sheet carrier density and how it is going to relate to the sensitivity of your sensor?
So what MPL have done, they've irradiated with neutrons and electrons and a number of particles, and found it's very, very insensitive. I mean, I think one reason is actually very simple. You've just got a monolayer, and most of the radiation passes through. So in a sense, that's one reason why it's insensitive to radiation damage. If you damaged it, then I guess you'll get point defects in the graphene, and we don't know how that affects the conductivity, and it's a good question. I suspect so, because you're bound to have some point defects in the graphene anyway, I think, when you grow it, especially large area. So I mean, it's worth, okay, let me make an important point, which is different from this. So what you read the textbooks and you read what papers say, and they say graphene is stronger than steel, right? 100 times stronger than steel. And so NASA invested, I think, $50 million trying to explore this idea that someone said, you have a geostationary satellite above the Earth, and why can't you tether it to the Earth with a graphene rope, as it were, because graphene is so strong? And they spent all this money, and that's because they're not good material scientists. But no, sorry, I didn't say that. That's because they didn't think. So pristine graphene is very strong because sp2 bonded and perfect. As soon as you make it bigger, you get defects in the graphene. You are bound to. And Harry Badisha pointed this out, who's this brilliant steel scientist. And you're bound to get defects. And these defects will limit the strength, as they do in other materials. And so you make something that goes from Earth to a satellite or something, and is chock full of defects. And it'll be no strong, it's probably less strong than steel. So the point defects are really important to consider in graphene.
Okay.
Yes.
Thank you very much, Professor Colin. I think I've taken up nearly all possible questions which have been shared in the chat section. So thank you very much, sir. And on behalf of the National Academy of Sciences India Delhi chapter and the host institution, the Dayal Upadhyaya College, I would like to thank you and all the attendees for sparing their valuable time and attending this particular webinar, and hope that your significant contributions, we can definitely listen again, maybe after a gap of a few months. So because it was really, I'll say, inspiring to how the research from the lab has been translated into a real application. And it is a step towards self-reliance and entrepreneurship altogether, right? Starting from one lab within a short span of 2 decades. So that's really commendable, sir. Thank you.
Well,
thank you very much.
Thank you. And thank you. And can I just say,
Sure, please, sir.
A great pleasure to talk to everyone, and to the students in particular, that these are great areas to work in. India's really investing in these areas. There's huge opportunities. There, I mean, on the graphene on saffron, so we don't understand the properties. There's just huge work to be done, fundamental research and application. So it's a wonderful area to work in. So I encourage you to work in this area, and you've got wonderful universities in India to do this in. So thank you very much.
Sure. Thank you. Thank you very much, sir.
Thank you.
Thank you. Okay. Bye-bye.
Bye. Bye.